For number 13, we are told that an air conditioner connected to a 120 volt RMS AC line is equivalent to a 11.7 ohm resistance and a 1.60 ohm inductive reactance in series. For A, we're asked to calculate the impedance of the air conditioner. And for B, the average rate at which energy is supplied to the appliance. First, we're going to look at A. And before we start working on the problem, we are going to write down everything that we were given. Our given is that we have a 120 volt RMS AC, which is equivalent to 11.7 ohms of resistance, and we have a 1.63 ohm inductive reactant. To find the impedance of airflow, we're going to use Z. And we have a formula for Z that we've used before. We last used it in problem 11. And we have Z is equal to the square root of R squared plus XL, which is inductance, minus X of C squared, which is capacitance. So this is the formula that we have. We're not given a capacitance, so our air conditioner unit does not have capacitance in it. So for our formula here, we are just going to X out the capacitance because we are not given it. If we rewrite this, it's just going to be Z is equal to the square root of R squared plus XL minus 0 squared. And if we reread the question, we see that we have a 1.63 ohm inductive reactant in series. Well, instead of this just being LR, this is actually X of L. So we can now solve this problem. We can write that our Z is equal to the square root of our R squared, and we know our R is 11.7 ohms. This is going to be in parentheses squared, and we're going to add this to our X of L, which we were given as 1.63 ohms, and that is squared. After we put this into a calculator, we are going to get approximately 11.8 ohms for our Z, and that's the answer for part A. For part B, we're asked for the average rate at which energy is supplied to the appliance. So for this, we are going to use a new formula, and this is going to be P, which represents power, and we're asked the average rate, so we're going to write it as P average. And this is going to be equal to the current times the resistance. Power is current, whatever is flowing through the appliance, multiplied by whatever resistance it faces. In here, our current is squared, and we are connected to an RMS AC line. So our current is going to be I subscript RMS. We can rewrite our I, because we know our I is equal to voltage over resistance, or we know this as I is equal to the alternating EMF over Z, because we don't have voltage. We are given 120 RMS, but this is actually the alternating EMF. We're actually skipping over this, and we are going to use this right here. Plugging this in, we can rewrite our formula as the P average is equal. We can write either the alternating EMF, which is E and then the subscript M, or the smaller m, or we can say V RMS over Z, and this is going to be squared, and it is times our resistance. From here, our average power is going to be equal to our VRMS, which is 120 divided by Z, and our Z we found as 11.8 ohms. We should also have voltage up here. This is going to be squared times our resistance, and our resistance is given as 11.7 ohms. If we plug this into our calculator, we're going to get approximately 1,210, and the units for power is in watts. And that is part B for number 13. For A, we established that Z is what we need to find the impedance of the air conditioner, and for B, we introduced a new formula, which is power, and that is the current flowing through the appliance times resistance. And we changed our I current to be the EMF, or the voltage RMS, and we divide that by Z, which we found in A, and multiplied that by our resistance.